now. So you should be able to share your screen.
Yes. So let me share my screen.
Yes.
Okay.
So yeah, thank you for joining us today. So we are honored to have Arup Chakraborty, I hope I'm pronouncing this halfway correctly, from Ventana Microsystems here today, giving a talk on RISC-V performance models. And Arup is a senior staff engineer with more than a decade of experience in system-on-chip architecture, performance modeling, and analysis and benchmarking. I'm just reading from your LinkedIn profile, as you can guess. And I'm really looking forward to your talk. So please go ahead.
Thank you. I am the chair of the RISC-V Performance Modeling SIG, and my colleague Newt from Sci-Fi, who is also there, Newt Lingard, he is the co-chair. So both of us have been, driving this SIG from last few months to create a performance model that a cycle accurate open source performance model that the rest of the community can adopt and use. And so we are here to talk about that effort, where that is, and how can we, take it forward, and where I think how it can be useful for the academic community as well for teaching and research. So with that, I will go to the next slide. So why are we doing this? As we all know, developing quality architecture, microarchitecture requires performance analysis, and performance analysis in turn needs a good performance model. And often, as it is the case, that maintaining, maintaining a good performance model is a time-consuming, difficult exercise, especially if each organization, be it, in the industry or in the academic world, if they have to do it on their own. And especially in doing so, we often have to go through the same path, before we arrive there. So we asked ourselves that, can we create an open source cycle accurate performance model that can run RISC-V binaries and instruction traces, something that can allow for some basic performance exploration out of box, and then can be modified sufficiently as needed by specific organizations to reflect their own custom architectures, and so on. So then, so we basically set out to do that. Like, we created a SIG, and the charter of the SIG has two main things. That one is coordinating and doing coordinating among its members and help create this performance model tool. And the second thing that is also relevant is that, okay, what trace formats we'll be using? Can we maintain a common repository of traces of certain interesting workloads that we all want to use? So we already have. So now currently so this is what we have currently. We have a Git repo, GitHub repo in the software RISC-V software space. It's called RISC-V Performance Model. It is a open source cycle approximate trace-driven performance model, and the processor that we have modeled is a simple superscalar out-of-order processor. Okay, and we will talk about that in a bit, in a couple of slides. But it's sort of a made-up architecture, but typical superscalar, and what you would expect out of a typical superscalar processor. And the model is based on a framework called Sparta. Now, Sparta has been around for quite some time. Like, it has been developed in the industry for like almost maybe 7 years now, say more than that probably. And now it is being used in multiple organizations. I think Barcelona Supercomputing Center, they have used it in their modeling. I know a couple of industry, like in companies use it, Sci-Fi among them, and there are others as well. We in Ventana also are starting to use it. So Sparta is a C++ based modeling framework that is used to create and run simulations. And in the next couple of slides, I will talk about Sparta, and then I will talk about the RISC-V performance model, where it is right now, and how can join the effort and help. So Sparta. So Sparta is essentially a framework. It's a set of C++ classes, structs, utilities that is used to build performance and functional simulation. It's a discrete event-driven simulation where the user have to define and schedule events explicitly, and simulation is considered to be done when when there are no more events to execute, or there is a way to halt the simulation as well. And Sparta consists of components by which one can define a simulation instance, define a hierarchy of components, define specific units and resources which are analogous to the hardware units that we want to simulate, have parameters by which you can configure this units. There are ways to dynamically configure your simulation, your model, and then there are a host of counters, stats, reports, logging, triggering mechanism, notification, etc. that is there in Sparta that can be used for the simulation. And finally, there are also this concept of events, where the events are there is a concept of ordering precedence between the events and these events and the schedule of the events. So, and the Sparta, why was Sparta developed? So the purpose is essentially that to provide a framework that on top of which any performance and functional simulator can be built. And it can, like, it's obviously ISA agnostic, like any ISA, any processor of any ISA can be built. And it was built in keeping in mind sort of a software development flow when it comes to developing these processor models. So using Sparta, it is fairly easy to, like, once you have different components, okay, it is fairly easy to connect them together, like CPUs, parts of the CPUs, memories of system, interconnect, etc. You can just, Sparta has this concept of ports, and if you connect, very much analogous to the hardware design, if you connect them together, okay, and it will just work, all together. And it is easy to switch out a part of the model and switch in as long as the ports are same. The rest of the model system does not care. So Sparta, there is more information out there on Sparta. There is a GitHub repo, and if you go there, you'll see a lot of activity there. Okay, and there is an overview of Sparta. And we are not going there today. It's a talk on its own, and if needed, we can do that. And there's also API documentation if you want to take a look at that. But this picture kind of shows like what's there, like in one slide, that there is a scheduler on the top. There are some events. on different types of events. There are statistics counters, there are ports, and there are three nodes which is where the components sit. And there is an instance of simulation, that is, there is a simulation class which is instantiated for a particular simulation by the user. There are some command line utilities, and then for a given simulation, we have to sort of do the create the main, which creates the simulation instance, and use the rest of the classes. So, for example, in the RISC-V performance model, the parts that are blue is actually in the RISC-V performance model. The rest of the things comes from Sparta. So essentially, it makes it like, because the takeaway here is that because there is this rich sort of framework, fairly rich framework behind, it is easier for to write any simulation on top of that. So now I'm going to talk about the model itself, the model that we are developing as a part of the SIG. So as I mentioned earlier, it's a C++ model that uses this framework and models a superscalar out-of-order processor and memory subsystem. And it does not represent any current RISC-V design. It's sort of a made-up design, that we put together. And the intention here is to create something that works, and then allow the community to take it, use it, and extend it, as needed. The sort of the block diagram of the model processor kind of looks like this, which is typical of what you would expect for the superscalar processors, that in order fetch, decode, rename, in order dispatch, and then out of order execute, and finally in order retire. So there are all these blocks there. Currently, many of the blocks have minimal functionality. The fetch, for example, it does fetch instructions from a trace, and the instruction comes pre-decoded, and then these instructions are pushed down the pipe. Now the pipes, all these blocks have flow control already inbuilt, so there are already stalls, etc., that can happen. So when the instructions, for example, reach dispatch, the branch instruction actually sent to the branch pipe, the load store instructions are sent to the load store pipe, and so on. So it can do all that already. There are certain things that it cannot do, like, for example, some of the units are not pipeline, which is not ideal. Like, so those are the things that we need to improve. There is, for example, we are still working on branch prediction. The rename at the stage is not fully done. So there are areas that we need to improve. The memory subsystem needs to be there as well. But the overall flow control and sort of the framework of this particular model is there. A certain framework is there on top of which we have to add on new functionality. So now, what's the current status of the model? So if you clone this model right now today, this is what you can do with it right now. So there are included in the repository, there are 3 architectures, a small 3 cores, essentially what we call. There is a small core, medium core, big core with different dispatch width, different ALU, ALUs, and so on. So it has been pre-configured, so that those with 3 different cores in sizes in mind. Now we have a sample dry stone trace, and there are instructions to make your own trace. Then we can run this trace on these 3 different architectures. And apart from that, you can also, like, there are parameters, etc., that you can change specific parameters that you want to change, that you can also do. But if you run it on these three particular cores, you see that dry stone performance improves as expected. So that's a sort of a validation of that the model is working today, even with this limited functionality. And since we are built on Sparta, there are certain functionalities that we almost get for free. That there is this functionality of visualization, pipeline visualization, where we can see how the instructions are flowing. There are a number of reporting mechanisms where you get the report of the stats from the beginning of the simulation or after a warm-up or on a time period basis, on a time series kind of data. We can already get that. So there is a more extensive demo that so we have a extensive tutorial and a demo, more extensive. So that's the tutorial is there in the GitHub repo that we have, and you get this demo in the RISC-V Summit. So I'm not going to repeat that because that's a longer talk, but I will send out the link to that demo, and I'll show a portion of it in this talk if we have time. So yeah, so now so right now, as I said, that we have some functionality in the model, and a couple of people are working on this to improve it and add new features. But I mean, so when I went to the RISC-V Summit to talk about this, we met a couple of professors, and they were interested in this effort, and I thought this will be a good opportunity to let the wider academic community in the RISC-V to know about the existence of this effort. And I feel like this will be a good opportunity if you can use the model, and rather than create your own model, use this model, and then if there are we have already identified certain work that needs to be done to this model, and on top of that, if there are things that you would want to add to the model for your teaching or for your research, please come and talk to us, and we'll see how we can get it all together in the model. So that's pretty much what I have right now. I also want to show you the tutorial that we have. So so this is our repository, and if you go to the wiki page here is a tutorial, and more detailed tutorial on how to use this model and so on. So I'm going to in next few minutes, I'm going to show you portions of the tutorial. Okay, instead of going through the entire thing, I'm going to highlight portions of the tutorial which I think is more interesting right now. So we use right now Sparta uses the RISC-V model, which we also called Olympia. The Olympia uses a trace format called STF. The STF, I think it stands for simple trace format or Sparta trace format, something like that. But essentially, it's a binary trace format. So there are ways to create that trace, and there is a library that using which you can create that trace. We have instrumented this functional model Dramajo to create that, and that's also part of this repository. And so we already have the dry stone trace, and there are, but we can create other traces as well using these instructions. And then there are a few utilities by which this trace can be sort of examined, like for example STF dump, which dumps out the content of the trace, and as you can see that it shows that the load stored various instructions, and there are metadata like for load, it is showing the address and the data. Data is not captured in the trace, I think. Then there are other utilities like IMEM instruction memory.
Please, I have a question. Can you make a font a little bigger, because it is very, very small?
Okay. Yeah.
Thanks.
Yeah.
Yeah, great.
Is this better?
Yeah, yeah, okay, it is.
Okay. Yeah, thank you. Thank you for telling me. So as I was saying that, there are other utilities too. Like, for example, there is already a utility by which you can see what is the instruction mix of my trace, or this is an sort of an IMEM is an utility that kind of gives you what the binary looks like a sorted memory, so that the instructions which are sorted by their memory address. So it's kind of like how the original binary would have looked like. Then there are other, like, apart from Sparta, this STF, the Olympia can run a JSON form of a trace. So like this JSON, it can actually consume as a trace, but for many number of instructions, it will be difficult to create this JSON. So we don't typically use it, but one can use it if one wants to. And then when we want to run the trace on Olympia, this is how we run it. Where you specify the workload, and with the model executable, and if you have this auto summary on, then it will show you a bunch of stats. Okay, from each of those units, like fetch, decode, dispatch, and so on. Like, it will show you stalls, etc. And there are, like, each of these blocks also have parameters, right? And so if you want to examine the parameters, you can do that. Like, let's say that no run, show me the parameters, okay, or dump the parameters into this YAML file, and then you examine the file, and so on. So these facilities are all there. And then if you want to change one specific parameter, that can be done. Like, basically from the command line, you can change the parameter and run the simulation, or you can create an YAML file where you specify those parameters, okay, and then use the YAML file to run the simulation. Then, as I was mentioning, there are certain this concept of architectures, predefined architectures, which a big core, medium core, small core, and those are YAML files. And the big core, for example, is built on top of the medium core. So it has medium core and then some changes on top of that. So now one can run the simulation like Olympia, just specifying the architecture, and that would also be another way of doing the simulation. Now, for all of these, there are various ways to generate reports. Okay, so by reports we mean essentially the stats. Okay, so there is a report definition file, there is a report content file. You can look into that. That's a little more detail. You can look into that, but I'll show you the sort of the basic output of that, capability of that, like what you can get out of it. So for example, like you can get stats for your entire model processor, like basically from the top. Okay, the top is the top of the processor, typically the same name that people use for their hardware processors configuration. So you can get the report for this entire processor, or you can get it for an individual block, like you can just get it for the dispatch or ROB or 0 or something like that. So it would show you the reports specifically for the block that you request or specify in the command line. Then the report, in the report definition file, you can specify that, okay, do I want it from the very start, or a certain instruction, when a certain counter has reached, let's say cycles have reached a particular value, then only the report will start. Okay, so that you exclude the warm-up portion, which is what is going down here, that when the retired number of instruction is greater than a certain number of instruction, then the report will be generated. And then there are also time series reports as well. So I think this is one example of the way the warm-up. So these are the two sort of reports, and if we compare, you'll see that, okay, one has the higher number of instructions than the other. And then there are some more sort of interesting things that can be done. Like, for example, for dry stone, we often want DMIPS per megahertz for dry stone. So you can actually create a report that defines that stats, okay, by saying, okay, I want this particular stat named DMIPS per megahertz, and it is defined. This is how it is defined based upon the IPC. So and then you can use that for. Then what if you then do the simulation and look at the report, then you would see that it would directly print out your DMIPS per megahertz along with other stats. And so this is one sort of exercise that we did, like essentially, okay, now run the simulation with this report for these 3 codes, like the default, which is the small code, medium code, and the big code. And you'll see that the DMIPS per megahertz number increases. It increases by a small amount because, again, I said that it's a very minimal architecture right now, but it shows that it is increasing. And as I mentioned, that there are time series reports that can be generated. So there is this thing called pipe out, which is a pipeline visualization, and so using Sparta, you can generate pipe out, which are text files, and then there is a viewer which uses those files, okay, to generate a pipeline visualizations, and you can see the instructions flowing through. And this is the part where I want to show Newt's demo the portion from Newt's demo, and I'll do that just at the end of this talk. So now, one of the things, so as I said that, one of our goal is to have this model which can do some basic performance analysis. So, and even though this model is put together quickly, it doesn't do a whole lot of things, but you can still actually do some analysis with it already, in the sense. So this is an example that basically, so we run, for example, here we are running dry stone on the small code, okay, and we get a certain DMIPS per megahertz. Now we want to see that, okay, can we improve on it, or where are the stalls? So we examine, for example, the stalls at the dispatch, and you can see that, okay, we are getting stalls because the ALU is back pressuring and the LSU is back pressuring. So these are the two main sort of dispatch stall reasons. Now we know that in this code there is only one ALU, okay, and dry stone is an it's an integer intensive benchmarks. So what we did is that, okay, so now let's see if we can increase the number of ALU. So we increase the number of ALU, and so yeah, so this is the part where we, there are some parameters related with rename. So I'm ignoring that for the moment, but as I said, that we increase the number of ALU, and then if we run that again on the model, you'll see that the ALU stalls are gone. So these are the things that we can do with the model currently. And you see that the DMIPs have increased slightly and so on. Now, with that, I want to show up a portion from new talk where talks about the pipe out visualization. Okay, just so, and that will also give us an idea of where what the model can do right now and what's its current status. So let me know if you can hear the sound. If you cannot hear the sound. Okay, so let's see. Use a lot of this you get the free pipe out collection. You can add more things to pipe out collection. The idea is easier to do with the SPDs and things. They're essentially collecting data directly out of the server. This is the examples of how to actually generate those pipe outs. And I shortened them down to 1,000 instructions. Can you hear it?
It's a bit difficult to hear, to be honest.
Is it difficult to hear, or
at least here, yeah. So is this video online actually somewhere?
Yeah, it is online.
So maybe it's a good idea to just post the URL in the chat, and so everyone can watch it later, if that would work for you. Because I guess otherwise it will be a bit difficult to follow the speaker.
Okay, that's fine. Yeah, I think I can do that. And so in that case, that's all I had for the talk. And yeah, so I can take I can take some questions.
So Arup, if you want me to, I mean, you have the visualization up there. I won't go through the entire talk that I gave, but I can at least briefly talk about what folks are seeing on the screen.
Yeah, I think that would be great. Yeah.
Okay, sure. Yeah. So first, my name is Newt Lingard. Oh, put that back. Put that back.
Oh,
put that back, Arup. My name is Newt Lingard. I am a principal performance architect at Sci-5. I am the lead maintainer of the Sparta Modeling Framework, and also co-chair for the SIG, for the performance modeling SIG, where we're building this performance model. Olympia. So the RISC-V Performance Model called Olympia. One of the things it can do is, lots of things it can do, but of course, Arup went through a lot of those things briefly, jumping over the tutorial. And we are working with some folks from the academic industry to see what we can do to actually improve and increase the accuracy of the model, or at least the extensibility. The main purpose is to add lots of flexibility to the model, allow different types of research analysis, be able to let folks, for example, if they had somebody who is on your team who's interested in doing prefetching analysis work, branch prediction work, cache level hierarchies, dispatching algorithms, whatever type of research development that they're doing in their academic industry, that this model can be extended to support that. The whole point is to move out of the way all the frustrations in startups to doing these types of things are essentially already solved, where you have essentially tracing of workloads and applications that you're interested in analyzing is already done. You have your workload analysis complete. And all you're interested in doing is just augmenting an existing performance model to do that work. It's very simple to some of the old concepts we've done with older simulators like Simple Scalar, and there's the QEMU simulations and things like that. We're all familiar with those. Sparta is more or less takes a more abstract approach to that and uses traces instead of functional execution behavior like Gem 5 does. So you don't have to functionally get it right. You just need to analyze the performance. And of course, you got simple scalar, which is pretty older simulation, but I would argue that this is a little bit more powerful. The fact that the type of flexibility and analysis you can do is it's like the next level of simple scalar type of work. So that's the direction we're heading with this. And we've been using it in the industry for many years, as Arup said. It's got a lot of engineering time behind it from folks who've been doing modeling and simulation for 25 and 30 years. But let me show you let me explain what you're looking at here. One of the things that the Olympia simulation can do, very similar to if you're familiar with doing anything with Verilog or RTL simulations, you can get waveforms and of course look at box waves and things like that. And that's essentially how most of the RTL development is done and how they do a lot of their debugging. We can do something like that. We can generate, well, our model cannot generate, but we could add support to generate BCD concepts and things like that. But we chose not to, instead to do something more of an abstract approach. On the left-hand side, which is very fuzzy, is essentially the original small core design. And what it has is it has one ALU, which is right about here. Each one of those colored boxes essentially represents an instruction that's going through. Time is essentially linear going this way. So what you're seeing is at any given time going straight up and down is one cycle of execution. So between these two black bars that the current red arrow is on is time 0. Everything to the left of that black bar is what happened in the past. Everything that's to the right of it is everything that's coming up in the future. So you can kind of get a bird's eye view of what is going to look. It's very similar to waveform, bird's eye view of what you're seeing that's coming up. You can see in this drawing is that essentially this is the ALU pipeline and it's completely saturated and packed with instructions. And hence that's why when Arup is showing you that the integer side, the dispatch block, which is up here, is completely blocked, waiting on essentially the ALU to be draining. And you can see that the color lengths for each one of those instructions sits in the dispatch buffer a long time. Now, if you add an ALU to it, what you can see is a distribution of the ALUs. These are 4 ALUs, if I remember correctly, what the big core is. And you can see the distributions of the instructions going across all ALUs. And you can also see that the impact up here in dispatch has got shorter color bands. In other words, each one of the colors, which represents an instruction, has gotten significantly shorter, meaning that dispatch is able to get through instructions a lot faster. But there are stalls, like up here, you can see that essentially rename is blocked and then most likely decode is being blocked as well. And what those instructions are, without really looking at the fuzzy picture here, most likely those are the load store instructions that are now being blocked and are waiting essentially for load store resources to become available for them to be dispatched. So the idea is that you bring up something like this, a pipeline tool, and you're curious what's going on. You're wondering where the performance bottleneck is. You can visually immediately see that you'll have some instructions that are just sitting there in different buffers or queues, and you can scroll down, up and down in this view, and you can see that, oh yeah, where they need to go is completely saturated. It gives you ideas such as, the poor man's approach to a lot of these things is to go ahead and increase those resources, double the size of the buffers. Well, that's great in a model, you can do that, but in RTL, that introduces area and timing and power constraints. So that may not be the right thing to do. So those are the type of things that as you essentially work with students and so forth, you can communicate to them. It's like, yeah, you could do stuff like that, but here are the repercussions of that, and have them understand it. And then the idea is to take a step back and don't necessarily just explode everything into large sizing, but maybe potentially do something clever, even going all the way back to the compiler. So the idea is that if we can change the compilation of the instructions in which they're ordered, could actually impact how the buffer allocations will be used inside the core. And you could run 2 different runs of the same picture, the 2 rainbow charts, so to speak, side by side of a different compilation of the workload. Or you can try different algorithms to see how well you can do with different dispatching. All kinds of things. So the idea is that more data that you have in your hand, the more visualization or even just more report data that comes out and is in your hands, empowers you to essentially make better decisions faster. And that's what we are striving to share with the industry and try to get better processor development going across the board. So any questions on this stuff?
All right, thanks a lot, Arup and Knut. Yeah, if there are questions, just raise your virtual hand, please. Or just, I mean, we're not that many, just open your microphone and start speaking. So I have a question. Oh, sorry, please go ahead.
No, go ahead, Michael. I have an invitation, but that can be the last, last item. This present.
So this looks really impressive, especially that you can do the visualization. Can you give us a bit of a background how this C++ approach you're building compares to a System C approach of modeling a CPU in terms of level of abstraction and similar? Because I've seen several like System C models, like the ones by Rolf Drexler's group from Bremen University. But of course, that's just an academic prototype. And I guess you invested quite a bit more work into that.
So I can take that, Arup, if you're all right with that.
Go ahead.
So that I knew that question was essentially during the RISC-V summit was going to be proposed as well. Both System C and Sparta are C++ frameworks, and System C is just defining it essentially a set of structures to be able to build a simulation based on a topology that you want. One of the frustrations, we started with System C, but interestingly enough, the Sparta Framework stemmed way before System C came onto the field. And so the idea was, as the System C was coming online, we noticed essentially what are some of the benefits, what are some of the drawbacks to that framework in general compared to what we were building. The extensibility was the number one frustration that we encountered with System C. It's very much static, global, so to speak, hierarchical definitions where you can't really easily, without having to do a significant amount of work, be able to change topologies and be able to modularize your blocks very simply. With Sparta, you're a little bit more, you're more able to do that. You can actually take for example, a decode block as it is. The decode block has no knowledge at all in the Sparta framework of where instructions came from and where those instructions go. So when it receives instructions to the concept of a port, which is very similar to System C. System C uses ports that actually exchange interfaces. Sparta uses ports to exchange transactions. And so the idea is that Sparta's transactions that come into it has no idea where they came from. It could come from a unit test. It could come from the fetch block. It could come from another topology that you decided to put maybe a block between fetch and decode, maybe a pre-decode cache, something like that. It doesn't know and it doesn't care. And that's the whole point. It allows you to be able to build a decode block that focuses purely on decode, decodes instructions, and then sends them down to its write port saying, I send these instructions out. I have no idea where they go. And it's done. So the idea is that you can build topologies dynamically and rapidly. There's a small core, big core, medium core could be done just by simply looking at some YAML files and just simply running through a different a set of for loops, basically say, how many LU blocks do I need to create? And you just keep going. The other aspect of Sparta adds the concepts of parameters. It was something that I was part of the System C task force a while ago to do with parameter-based hierarchy in System C. I don't think it ever got any traction and went anywhere. I don't know. I kind of lost track of it, to be honest. But the parameter aspects are not really clean. And being able to parameterize and identify and explicitly set behaviors on individual blocks. And that's something we definitely addressed in Sparta to make sure that was done up front, because the very first thing you do in any kind of research, no matter where you are, is you want to be able to tweak topologies and parameters and behaviors of individual blocks to see how it affects your workload analysis. And that's super, super simple with Sparta. I don't know how to do that without having to basically create an entire parameter infrastructure on the side for a System C type of model. Another difference between them is that, and a big difference, is Sparta allows for you to be able to define precedence behaviors between events and behaviors. So if you want to absolutely guarantee a certain behavior in your Sparta model, because it's an event driven and it's timed, if you want a certain event to always occur before another event occurs, Sparta makes that easy. You explicitly tell the framework, this event must and forever always come before that event, and don't ever let them be swapped. And it will make sure that that's adhered to. When it's adhered to, the idea is if you as a modeler try to break the rule, the framework will stop you immediately, telling you you cannot schedule that event before that event had already fired. You cannot do that. That's very important when you're trying to do modeling things such as a MUX. And in the Sparta example tutorial that Arup talked about at the beginning of his talk, I do have an example of how Sparta solves essentially the MUX problem. Multiple inputs, unclear when those inputs come in, so you can make a determination when you should do selection and drive the final output. System C solves that with the delta cycle and just essentially does reevaluations. We didn't see that as necessary, considering in simulation, especially in Sparta simulation, all the events up front. You know which events are going to be used and what events will be scheduled and which events will be moving forward. So it's a completely different modeling approach. One thing I might argue a little bit on as far as the last bit is that Sparta is about 4 or 5 times faster than a System C model. That's another thing that I've encountered when I've done some System C models and I converted them over to Sparta, especially as some other companies I've worked with have done that. They've noticed a dramatic improvement in performance, getting the exact same results. And then the last thing I would do is Sparta has a very powerful report mechanism that allows you to do statistic collection mechanisms that just work with the framework. So you can explicitly document how you want your reports to look, how you want your warm-up periods to look, how you want trigger points are, what kind of reports you want to do. It's all part of the framework. You don't have to add anything on top of it. And then the last thing, and I'll let it go, is I keep saying that Sparta does work with System C. So if you have a System C model that you want to interact with Sparta, there are System C enablements in Sparta, as well as TLM examples where you can illustrate how you can integrate a TLM based interfaced model to a System C model. And then that mode, System C, is the master of simulation. It refuses to not be. And so we said, that's easy. Sparta is a modular-based framework design. It was designed from the ground up with the requirements being that it must be able to work in a co-simulation environment. So it can be slave to, for example, a System C scheduler. There's only one caveat to a System C Sparta model. You can't do 0 cycle based send and request and expect it all to work within the same cycle, because Sparta doesn't understand or know the concept of a delta cycle. And at the same time, the schedulers must be sequentially advanced. And I can go into if anybody ever asks questions about that, I can go into detail. I tried to solve that problem, but it's a really tough one to solve. But so sorry, it might be a long answer for System C, but
that's perfectly fine. Thank you. Yeah, sounds like a definitely interesting problem to solve. But I guess we will go into detail here unless somebody's really interested. One thing I would assume that is this would also be a great approach to use Sparta and the RISC-V models to experiment with like instruction set extensions for accelerators and stuff.
Yes. So one of the open items that we have actually on the Olympia RISC-V performance model is adding the vector extension. The decoder is quite capable of doing it. It's just adding the understanding to Olympia to know what a vector instruction is and to instantiate vector units and to define your own latencies, what those are, define pipelining behaviors. All that work needs to be done. It's one of the open items in the performance model. That's an example.
Well, sounds pretty good. I'll definitely take a look. Great. So any other questions? Raphael, you had a comment, I guess?
Yeah, so it's an invitation. So for everyone here, we started the RISC-V technical sessions where anyone can present. And I see that some of the topics that were presented today are a great fit for the broader audience, because we send an invitation to all the members and everyone can join. I mean, students, professors, developers. So if you want to present, I'm going to paste the link for that in the chat right now. Yes. Feel free to pick a date that fits your calendar and just submit a proposal. Then we can add you to the agenda for presenting.
Great, thank you. Yeah, that sounds interesting.
Yeah, that sounds good. Yeah, we will take a look at that. Thank you.
Great. So maybe one thing, Arup or Knut, could you post the link to that video you were trying to show? Actually,
yes. that is-
chat so we can send it along for people who want to watch.
I will do that. So if there is no other question, I'll just end with this point that today, let's say one of your students or you want to, if you want to, investigate some branch prediction algorithm or certain cache replacement policy or something like that, you can start with this model as is. Okay, as you can see that it can, accept some instruction from traces, do some sending them through the pipeline, doing some out of order execution, returning, etc. So that's the basic framework that is ready. On top of that, you can add your branch prediction there, and you can then see, okay, how does that improve the performance? So the basic point is that you don't have to, if you want to investigate just the branch prediction, you don't have to write the entire thing. Okay, that is sort of what we are trying to enable.
Right. Yeah, that's great. And especially modeling like memory hierarchies, cache behavior. I think that's one of the biggest performance impacts, especially on multi-core architectures. So that will be really useful. And I guess that's quite a load of work to do in either System C models or Jump5 based simulators. So yeah, definitely sounds like a good use case.
Okay. Yeah. Thank you for thank you for the opportunity to give this talk. And if you have any other feedback, I will send out the links as well. And if you have any other feedback, any questions, either contact us back here through this SIG or in our GitHub. Either way should be good.
Great. Thanks a lot again for presenting today. This was really interesting. So looking forward to meet you again in a future RISC-V meeting. So if there are no more questions, I would say we can close the session today, unless there's some other things you'd like to discuss. So I'll stop the recording now.